Okay, so let's continue on with Chapter 5. This is Lecture 3. And we're going to start by doing example 5.15 in the textbook, which is on page 206. So if you look at this example, turn your book to page 206, and you can read example 5.5 with me. It's basically an example of Dalton's law. If you remember in part 2, we left off talking about Dalton's law of partial pressures. So example 5.15 reads, mixtures of helium and oxygen are used in scuba diving tanks to help prevent what is called the bends. And the bends is essentially when what happens is if you are using an oxygen tank under pressure down below the surface of the ocean, because the pressure of the ocean, the weight of the water puts so much pressure on your skin, it changes the pressure of your blood inside your body, which then changes the concentration of oxygen in your body when you breathe through an oxygen tank. And if you rise too quickly, when you're at depth in the ocean, what happens is the pressure on your skin will lower at too fast of a rate and cause your blood to have too high of an oxygen concentration in it, and it causes severe pains and aches, and I think it can actually kill you, and that's what the bends is. Okay, so to prevent that from happening, they use a special mixture of gas in the scuba tanks. So for this particular dive, we're told that 46 liters of helium at 25 degrees Celsius in 1 atmosphere and 12 liters of oxygen at 25 degrees Celsius in 1 atmosphere are pumped into a tank that has a volume of 5 liters. So that volume of 5 liters, that would be the tank that's on your back during a scuba dive. And we're told to calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees Celsius. Okay, so using our normal scheme, let's go ahead and write out what it is that we know. So we know, for example, that we have a volume of oxygen that's equal to 12 liters, and this volume of oxygen is pumped into the 5-liter tank, coming from a source that's at 1 atmosphere of pressure and a temperature of 25 degrees Celsius. Likewise, we know that there's a volume of helium, 46 liters, and this is being pumped into the scuba tank from a source that's at a pressure also of 1 atmosphere and a temperature of 25 degrees Celsius. Okay? And what we're asked to find is the partial pressures of oxygen and helium in the 5-liter scuba tank. Okay, so I also often find it helpful to visually draw what's happening, and so we call that a model. And it can be a very simple diagram, but just something to show what's going on. And so we essentially have a large volume of helium. And so this would be our helium, and it's a volume of 46 liters at a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. And then this is added to a smaller volume of oxygen, and this volume is 12 liters, and the temperature is 25 degrees Celsius, and the pressure is 1 atmosphere. And then this goes into a scuba tank, where what we know about the scuba tank is that its volume is equal to 5 liters. And we know that the temperature of the mixture of oxygen and helium is equal to 25 degrees Celsius. So in addition to finding the partial pressures of oxygen and helium in the 5-liter scuba tank, we also need to find the total pressure. Okay, so how do we go about solving this? Well, we can, for example, recognize that our gases are behaving as ideal gases. And really, this is an assumption. If you're wondering where I got that from, then just know that what I'm really doing is I'm just making an assumption. I'm saying, well, I know that if I can treat these as ideal gases, then it allows me to say that PV equals nRT. And this then allows me to say that I know what my volume of the tank is. I know what my temperature of the gases in the tank is. I know what my R value is. That's just the universal gas constant. What I don't know is I don't know pressure, and I don't know number of moles. But if I recognize that I have a helium tank, and in my helium tank, I can also say that the pressure of the helium times the volume of the helium equals the number of moles of helium times the gas constant times the temperature of the helium. And when I look at what I know about my helium, I actually know what my pressure is, I know what my volume is, I know the gas constant, and I know what my temperature of the helium is. And so I can use this equation to find the number of moles of helium, which is just equal to the pressure of the helium times the volume of the helium divided by the gas constant times temperature of the helium. And likewise, I can do the exact same exercise with my oxygen tank. So for the oxygen, again, I know the pressure of the oxygen, the temperature of the oxygen, the volume of the oxygen. And so I can use the ideal gas equation where the number of moles of oxygen is equal to the pressure of the oxygen times the volume divided by the gas constant times the temperature of the oxygen. So how does that help me, though, with this first equation that I wrote up here in terms of my actual scuba tank? Well, recall, just before we ended our last session, we said that the law of partial pressures, Dalton's law of partial pressures, allows us to say for an ideal gas that the total number of moles in that ideal gas is just simply equal to the sum of the individual components in that ideal gas. And so I can say that the number of moles in my scuba tank for this example is simply equal to the number of moles of the helium plus the number of moles of oxygen. And I know the number of moles of helium, and I know the number of moles of oxygen. So I can determine the number of moles in my scuba tank, which now gives me this N in my ideal gas equation, which then allows me to solve for the total pressure. So let's go ahead and do it. So the number of moles of oxygen is, again, this equation here, where it's the pressure, 1 atmosphere, times the volume, 12 liters, divided by the gas constant, and we'll use the form that is 0.08206 liters atmospheres over Kelvin mole, times the temperature, which is 25 degrees C, but be careful, It needs to be absolute, so I add in the 273.15 to make it then Kelvin. And I use my calculator to figure this out, and I get that the number of moles of oxygen in my scuba tank is 0.49 moles. Likewise, I can say that the number of moles of the helium is equal to the pressure of the helium. So I'm using this equation here now. So it's the pressure of the helium, which is 1 atmosphere, times the volume of the helium, which is 46 liters, divided by the gas constant, 0.08206, times the temperature of the helium, which is, again, the 25 degrees C plus 273.15, which is 298.15 Kelvin. Plugging this into the calculator, we get that the number of moles of helium is 1.9 moles. Okay, now, this is the number of moles in my scuba tank of oxygen. This is the number of moles of helium in my scuba tank, right? So going back up to my diagram, the number of moles of helium that was added to the tank is 1.9 moles. The number of moles of oxygen added to the scuba tank was 0.49 moles. So in my scuba tank, I can say that I have 1.9 moles of helium and 0.49 moles of oxygen. So to answer the first part of the question, which is what is the partial pressure of the oxygen and the helium, well, I now go back to my first law equation, where I can say that the partial pressure of the oxygen is equal to the number of moles of oxygen in the scuba tank times the gas constant times the temperature in the scuba tank divided by the volume of the scuba tank. And so plugging all these numbers in, we get 0.49 moles times the gas constant 0.08206. You'll have that one memorized by the end of this chapter. Times the temperature, 298 Kelvin. And this is all divided by the volume of the scuba tank, which is 5 liters. So the partial pressure of the oxygen in the scuba tank is 2.4 atmospheres. So that's the answer to the first part of the question for oxygen. Now we have to do the same for helium. So the pressure for the helium is the number of moles of helium times the gas constant times the temperature in the scuba tank divided by the volume in the scuba tank. And so this equals 1.9 mole times the gas constant, 0.08206, times the temperature, 298 Kelvin, and this is all divided by 5 liters. And so that then equals 9.3 atmospheres. And so that is the partial pressure of the helium in the scuba tank. Okay, now the final part of the question is the total pressure in the system, or the total pressure in the scuba tank. So this is P total, which is the same as P scuba. And again, based on Dalton's law of partial pressures, we can simply say that this is the sum of the individual species, their component pressures in the gas. And so this is simply equal to the pressure of the oxygen plus the pressure of the helium. And so this is equal to 2.4 atmospheres plus 9.3 atmospheres. And this equals 11.7 atmospheres is the final or total pressure in that scuba tank. So 11.7 atmospheres, just to create some physical relevance for you on this, remember that 1 atmosphere is roughly 14.7 psi. So 11.7 atmospheres is somewhere around 1600 psi. So those scuba tanks are holding a high pressure. 1600 psi is a large pressure. Okay, let's go ahead and move on. And we're still in section 5.5 of Dalton's Law of Partial Pressures. So let's introduce the concept of the mole fraction. This is really important, and it's a concept that you're going to use all through chemistry and also into college if you study chemistry, engineering, and related fields. Okay, so first of all, what is the mole fraction? Well, the mole fraction is the ratio of a given species number of moles in a given mixture to the total number of moles in that mixture. And we use the letter X to indicate mole fraction. So mathematically, taking this language and converting it into a math expression, we can say that the mole fraction of species I, okay, that's the given species part, is equal to the number of moles of that species divided by the total number of moles in the mixture. So, for example, the mole fraction of species 1 is equal to the number of moles of species 1 divided by the total number of moles, which is equal to the number of moles of species 1 divided by number of moles of species 1 plus number of moles of species 2 plus ... all the way up to number of moles of species N, where, of course, as we said before, N is the total number of species in a mixture. Okay? Okay, now what's kind of neat about mole fraction is that since our ideal gas equation says that N is equal to PV over RT, which we can basically write as P times V over RT. I just pulled the pressure out from the numerator, okay? Then we can say that N1 is equal to P1 times V over RT, and N2 is equal to P2 times V over RT, and all the way up to N sub N is equal to the pressure of species N times V all over RT. And if we go to our mole fraction definition, where X1 is equal to N1 divided by N total, well, this is simply equal to N1, which is P1 times V over RT, all divided by N total, which is N1 plus N2 plus ... up to Nn. So N total is N1, which is P1, times V all over RT, plus P2, that's N2, times V all over RT plus dot 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 plus P sub n times V all over RT, that's N sub n. And we recognize that because my V over RTs all cancel, we have P1 in the numerator, and in the denominator, we just have P1 plus P2 plus dot 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 plus Pn, which is nothing more than P total. So notice that the mole fraction of a given species in a mixture is simply the partial pressure of that species divided by the total pressure in the mixture. So we can say X1 is equal to P1 divided by P total. Or to write it more generically, X sub I, mole fraction of species I, is equal to P sub I divided by P total. This is an important definition. You want to remember this. That's the mole fraction of species I. Okay, so let's go ahead and apply this with example 5.16. So if you could, turn to page 208 and read along with me example 5.16. So in this case, we're told that we have a partial pressure of oxygen that is 156 torr in air with a total atmospheric pressure of 743 torr. Calculate the mole fraction of O2 present. Okay? Well, again, let's start with what we know. We're told the pressure of oxygen, PO2, is equal to 156 torr. And we're told that the total pressure of the atmosphere is equal to 743 torr. And again, just to create physical relevance for these numbers, this 743 torr is basically the atmospheric pressure that we usually experience on any given day. Okay, that would be roughly the barometric pressure. Okay, so that's what we know, and what we're asked to do is to find the partial pressure of oxygen in the mixture. Okay? And that is, of course, X sub O2. All right, well, using this equation that we wrote up here, Xi is equal to Pi divided by P total. That would be our model. Pretty straightforward. So we can then say that the mole fraction of oxygen, XO2, is equal to the partial pressure of oxygen divided by the total pressure. And we know these two parameters. So the partial pressure of oxygen is 156 torr, and the total pressure is 743 torr. So when you plug this into your calculator, you find that the mole fraction of oxygen is 0.21. Or oxygen is roughly 21% of our atmosphere. So our atmosphere, the air that we breathe, is a mixture of gases, and roughly 21% of the air is oxygen. That's what we need. Okay? Okay, so just to sort of create some relevance for this new parameter, we could come back up to our old example and we could say, what is the partial pressure of oxygen in our scuba tank? Well, that's just XO2 is equal to PO2 divided by P total. And so this would be the pressure of the oxygen was 2.4 atmospheres, and the total pressure is 11.4 atmospheres. Okay? Likewise, the partial pressure of the helium in the tank is the pressure, or the mole fraction of helium in the tank is the partial pressure of the helium divided by the total pressure. So this is 9.3 atmospheres divided by 11.7 atmospheres. Okay? So I didn't calculate those numbers, but I just wanted to show you that we could, in fact, have calculated the mole fraction from the previous example if we knew the concept of mole fraction at that point. Okay, so now we can move on to the next section, which is section 5.6, the kinetic theory of gases. And the good news is that we've actually covered a large part of this. And so there's just a few things that I need to highlight from this section that we didn't talk about before so that you're able to do these types of problems. So first of all, what is the kinetic theory of gases? Well, it basically simply recognizes that if you have a system of particles, right, this system of particles has individual particles that have different velocities. So some are going in different directions. Some have really high velocities. Some have really low velocities. Right? And so you have these particles that with these varying velocities that are basically just bouncing around and bouncing against each other and so on and so forth. And so basically what we can say, and this is where the kinetic theory of gases becomes important, is that any object or particle that has motion, that is some kind of a velocity, so if the particle has motion, it has velocity. And if it has velocity, it has kinetic energy. That is the energy associated with an object being in motion. So how do we define kinetic energy? Well, the kinetic energy in general is defined as 1/2 times the mass times the velocity squared of that particle. So to write this for a specific particle, we would write that the kinetic energy is equal to 1/2 times the mass times the velocity of the particle squared. And so I'm using U here to indicate velocity so that it doesn't get confused with V for volume. And M, of course, is mass. KE is obviously kinetic energy. So when we write the units of this will have units of energy, which we in the SI system use the joule to indicate units of energy. And the way that this equation is written, this would be the unit of energy joule per particle. Okay, so just so that we're clear, J is a joule named for Ernst joule, and that is the SI unit of energy. Okay, now we can recognize that this is just the kinetic energy of one individual particle in the system, right? Say this particular particle here. I don't know how that ruler decided to appear, so I don't know how to get rid of it. Oopsie. Boy, I'm really messing up now. It's kind of neat, but I don't want it. Okay, there we go. So how do I get rid of the ruler? Yeah, that seemed to do it. Okay. Okay, so if we recognize that this is the kinetic energy of just one particle, here we go. This is the kinetic energy of just one particle, but we actually have a collection of particles here, right? So we have a system, which is to say that we have moles, okay? We have a mole of particles in our system. And so we would then say that the kinetic energy of a mole of our system of particles is equal to Avogadro's number, capital N sub A. And so this is the number of particles per mole. And this is what's equal to the 6.02 times 10 to the 23rd particles per mole. Okay? So the kinetic energy of a mole of particles is number of particles per mole times the kinetic energy of a particle, which we've already defined above, which is just 1/2 times the mass of that particle times the velocity of that particle squared. Okay, now if we go ahead and define what we call the average kinetic energy, so we define the average kinetic energy of our system to be equal to this kinetic energy of the mole, but recognize that the velocity of the particle is different for every particle. And so we introduce the idea of an average velocity of that system of particles. So the average kinetic energy is the number of particles in a mole times the average kinetic energy of those particles based on the average velocity. And so U bar ends up being the average velocity of the particles. Okay? So if we define the average kinetic energy in this fashion, we can show, not using this equation, but using a different technique that I'm not going to go over here because it's not that important. It's in your textbook if you want to review it. But we can show that the average kinetic energy is equal to 3/2 times the gas constant times temperature. Okay, so hold on to that idea for just a little bit. And now we're going to take a quick sub-segue, and we're going to define another concept, which we call the root mean square velocity, or U sub RMS. So that RMS stands for root mean square. Okay? So this URMS is the root mean square of velocity. Okay? And so URMS would basically be something of the nature where you have the root and then you have the square of the velocity, the average of the mean of the velocity. Okay? Okay, so we can then say, we can basically shorten this here and say that URMS, the root mean square, is equal to the square of the average velocity. Okay? Okay, now remember that kinetic energy from this expression here is equal to N sub A times 1/2 mu bar squared, but it's also equal to 3/2 RT. So we can say that we can set these two equal to each other. We can set this average kinetic energy equal to this average kinetic energy and get that the number of particles in a mole times the kinetic energy of that particle based on the average velocity is equal to the second form of average kinetic energy, so 3/2 RT. And so we have in here a component of our root mean square. So we can solve for this directly and say that u bar squared is equal to 3RT divided by number of particles in the mole, Na, times the mass. Okay, so notice that the 1/2 cancel. Now we can take the square root of both of these sides and get that the root mean square of our particles is equal to the square root of 3RT divided by n sub a times mass. Okay? And so in other words, this is all equal to this concept of root mean square of the velocity. Okay? All right, so I'm going to put a box around this because we're going to talk about this a little bit more. And just note, just so that you have some understanding of the terms that are in this equation, just remember that m is the mass of a particle. So this is going to have units of kilograms per particle. I mean, I say kilogram, but the mass is like times 10 to the minus 10th or something. And then Na is the number of particles in a mole. And this has units of particle per mole. Okay? So when you multiply these two together, like you do in the denominator of this expression, you get kilograms per mole. Okay? So n sub a times the mass is equal to the molar mass of that species, big M, with units of kilogram per mole. Okay, so the molar mass of diatomic oxygen, for example, is 32, right? 16 times 2 is 32. And so we can now write this expression of the root mean square by introducing the idea of molar mass and say that URMS is equal to the square root of 3RT divided by the molar mass of that species, capital M. Okay, now one thing that I want to draw your attention to, so there's a caution here. The R in the root mean square equation is as was provided in part 1 of chapter 5, where in this case, we're saying that we're using the value of R, where R is equal to 8.3145 joules per mole Kelvin. Okay, and just to kind of walk you through the units to show you why we have to use joules here. So if we do a unit analysis on the root mean square of the velocity, right? I do this based on units. Okay, so we have R in our expression, so that has units of joules per mole Kelvin, right? And then that's times temperature, T, which has units of Kelvin. And then this is all divided by M, which has units of kilogram per mole. Okay? And so, of course, our kelvins cancel and our moles cancel. And so we're basically left with units of joules per kilogram. And what is a joule? Well, the unit of a joule is a Newton meter. Well, what is the unit of a Newton? A Newton is a kilogram meter per second squared. Okay, mass times acceleration. Units on acceleration are mass per second, meters per second squared. Okay, and force, which is Newton is a unit of force. So force is mass times acceleration. So kilograms times meters per second squared is a Newton. And then what is energy? Energy is force through a displacement. So that's force is Newton times the displacement is meter. So a unit of energy is a Newton meter. And so I plug all of this in. So my unit of joule is a Newton, which is a kilogram meter per second squared times meter divided by kilogram, this kilogram here. And so my kilograms cancel, and I'm left with units of meter squared per second squared, which when I take the square root is just meters per second. And remember, this is velocity, which has units of meters per second. Okay? So this little exercise that I just took you through, that's what we call unit analysis. And it's extremely important for being able to keep track of your calculations and make sure that what you're doing is always making good and proper sense. Okay, let's now go on to our second to last section in chapter 5, which is section 5.7. And this is what we call effusion and diffusion. Okay, so first of all, what is the difference between diffusion and effusion? Well, generally speaking, diffusion is essentially the mixing of gases. And so we can visualize diffusion by having a tank. And suppose there is a, razor thin membrane that separates the tank in half. And on one side of the tank, one side of the membrane, we have oxygen molecules. And on the other side of the tank, we have nitrogen molecules. And then the membrane disappears. And we then have still our same tank. But of course, what's going to happen is the oxygen molecules are going to flow over to the right-hand side of the tank. Some will stay on the left. And then the nitrogen molecules are going to flow over to the left-hand side of the tank. Some will stay on the right. But you get the basic idea. The two gases basically mix in with each other. Now we can define something which we call the diffusion rate. And the diffusion rate is the rate that the gases mix. Okay? All right, so what is effusion? Before we get too further into this, let's now define what effusion is. And effusion is essentially the passage of a gas through a tiny orifice into an evacuated chamber. Okay, so again, if we want to visually draw this, we have a tank. And now there's a solid separation between the two halves of the tank. But there's this little tiny orifice that creates a hole in the plate separating the one side of the tank, which is evacuated. So this side would be what we would call a vacuum. And then on this side of the tank is where we have a system of particles of gases. And effusion is basically the flow of one of those particles from one side of the tank through the orifice into the vacuum. And one thing that was learned by a fellow by the name of Graham is that the rate of effusion of any given gas is inversely proportional to the square root of the mass of its particles. In other words, we can say that the rate of effusion is equal to 1 all over the square root of big M, inversely proportional to the square root of the mass of its particles, which is basically the molar mass. Okay, now we can also talk about Graham's law of effusion. So there's one more concept that I need to introduce, and then I'll show you how this is important. So Graham's law of effusion basically states that the rate of effusion of gas number 1 is proportional to rate of effusion of gas 2 and based on the definition of the rate of effusion, that would then mean that the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1 would summarize Graham's law of effusion. So what we want to do is we want to be able to show that this is true, that this result is true, based on the kinetic theory of gases that we just talked about in the previous section. Okay? So since the rate at which particles effuses past a tiny hole depends on its velocity, we can use the kinetic theory of gases that effusion of gas 1 divided by fusion of gas 2, this is Graham's law of effusion that I wrote up here, okay, is equal to, right, so this statement of here is saying that the rate at which particles effuse past a tiny hole depends on its velocity. So we're going to say that the effusion of gas 1 is equal to the root mean square velocity of gas 1, and the effusion of gas 2 is equal to the root mean square of gas 2. Well, based on our previous definition of root mean square from our previous section, root mean square is the square root of 3RT divided by the molar mass. And so we can show that this is equal to the square root of 3RT divided by big M1, the molar mass of species 1, and then URMS2 is equal to the square root of 3RT divided by the molar mass big M2. And so when we do the algebra, of course, the three RTs cancel, and we end up showing that the effusion of gas 1 is the square root, or is 1 over the square root of M1, and the effusion of gas 2 is 1 over the square root of M2, which means that the ratio of these two effusion rates, effusion of gas 1 divided by effusion of gas 2, is the square root of M2 divided by the square root of M1. And so why is this important? Because this result uses kinetic theory of gases to show what Graham had experimentally observed. So Graham came up with his law of effusion, this ratio of the rate of effusion of gas 1 to the rate of effusion of gas 2. He came up with that experimentally. And he arrived at this result that the ratio of these effusion rates is the root of the molar mass of species 2 divided by the root of the molar mass of species 1. But then later, the kinetic theory of gases was developed, and this idea of a root mean square velocity was generated. And by recognizing that the rate of particles effusing past a tiny hole depends on their velocity, we were able to use the kinetic theory of gases to arrive at the same result that Graham had arrived at experimentally. Okay? So, pretty cool stuff, and just shows how science works in tandem to arrive at its results experimentally, but also theoretically. Okay, so there's one more section. I am going to have to make a part 4 for chapter 5. So the next section will be section 5.8 on real gases. So I will get that recorded soon so that you can finish off chapter 5. Thank you.